if they want, I can send a copy. So this was example one. This example one here, we are going to use the angle-angle similarity postulate. And what we did is we showed that this angle T and this angle G, they were congruent, well, because they're both 61 degrees. And angle SHT is congruent to angle GHF because they're vertical angles, and vertical angles are congruent. And so by using this first theorem, if we have two angles of one triangle congruent to two angles of another triangle, then they are similar triangles. Okay, so let's go ahead and move on to the next one. Now the next two slides are just going to be theorems. So this one is the SAS similarity theorem, and this is for similarity. So side, angle, side. Now hopefully this is one of those moments where stuff that we've done in the past should help you understand what we're doing currently. Okay? So side, angle, side. That means we need to show, for example, that this side is to this side, that's right here, AB is to QR, as this side is to this side, that is AC is to QS. And we need to show that angle A is congruent to angle Q. So you can see that we have a side, an angle, and then another side. That's why we call it SAS. Now it is very important that you know that that angle has to be what we call the included angle. There we go. That's the word we want to, you might want to underline that word. It has to be the included angle, and that was the same rule when we did congruence. If you have a side a side is to one side as a second side is to a second side, and the included angles are congruent, this is called SAS similarity. We can then conclude that those two triangles are similar. So notice here, we are not using AA similarity. We don't know that angle B and angle R are congruent. We don't know that angle C and angle S are congruent. We're using something different in this example. This is called SAS, okay? Now, here's our third similarity theorem. Again, this is something similar to what we've done in the past. This one's called SSS. So here's what this one's saying. If AB is to QR as AC is to QS, as BC is to RS, then both triangles are similar. Now notice here, do we know anything about any of the angles being congruent? Nope. That's why there's no A up here in this one. This is SSS. So this is what we call an extended proportion. Remember we talked about extended proportions last week in section 7.1? In other words, we've got three ratios that are all equal. Okay, so now let's do some examples of these to see if we can get this solidified a little bit more. By the way, tomorrow when we meet as a class, our goal will be for you to actually kind of get your hands dirty and practice some of these things, AA, SAS, and SSS. In fact, let me write that up here right off the gate. We are going to use one of these three, or they're not going to be similar. Okay, because remember, the objective for this particular section is to prove triangles are similar. That's what we're trying to do. And right now, we have three ways to do that besides the definition of similarity. It says determine if the triangles are similar. If they are similar, complete. So this is very similar to the last example, but notice here, we don't have any vertical angles. Do we know that angle U is congruent to angle F? Do we know that? Well done. Yeah, it's right there. Right, so let's go and write that down. I'm going to say angle U is congruent to angle F. And I don't even think I need to explain that because they have the same measure. That's how we define congruent angles. Now guys, just using common sense, since I just said that I have an angle congruent to an angle, am I going to be using SSS in this one? So I'm just gonna, if you guys don't mind, I'm just gonna cross that off the list. That's probably not what I'm gonna use here. It's probably gonna either be AA or SAS. Do we know any other angles? Nope. So guess what? I don't think it's gonna be AA. Now, is this guaranteed gonna be the reason? Maybe. We need to be careful. Let's see if we've got that. So here's what we need to do. Would you guys agree that this is the shorter side? So I'm going to say that UW is to, now what's the shorter side on this one down here? HF. So I'm going to call it HF. By the way, it would be wrong if you called it FH, but I'm going to call it HF. We need to check to see, and I'm going to do this in a different color. This side here, which was UV, is to, and then this side right here, which is GF. Now guys, I'm a geometry teacher, so I'm going to be like over the top showing all kinds of work on these. You don't necessarily have to write all this stuff, but I'm trying to make sure I write it down because I want you guys to be able to take good notes and go back and look at these things. All right? All right, so now what I'm going to do is I'm going to substitute the stuff in that we know, okay? So what was UW? Well, I think it was 9. What was HF? Well, I think it's 21. And by the way, what I'm saying is these mean lengths, right? So that's what we're talking about. What's the length of UV? Well, that's 18. What about GF? 42. How do we check to see if this is a true proportion? So now what I need you to do, if you've got your calculator, I'm going to let you do this step. I want you to take your calculator, and I'd like you to cross multiply those and see if they are indeed equal. In fact, I'll do it too. You could do that as well. You could reduce. In fact, you could reduce 9 over 21. You don't have to, but you can. Interesting. So when I cross multiplied here, I got 378 equals 378. And again, I just used my calculator. If you wanted to reduce this, you could. In fact, I'll talk about that here real quick. But here's my point. Did we just show that these sides, this proportion that's based on the ratio of these sides, did we show that that is indeed a true proportion? Check. So this is the S and the S. So we've got SAS is the reason that these guys are similar. The last thing we got to do is write a similarity statement. Now I'm going to let you try to write this one on your own, okay? So triangle FGH is similar to what? Write the triangle there that you, remember the order of the letters is important. Triangle FGH is similar to what? Let's fill that in. I have UVW. You guys agree with that? Now, guys, I'm just telling you right now, I can already predict that in a future quiz, you see it, there's going to be a question, and it's going to be maybe even a two-parter, and it's going to say, why are these two triangles congruent, or I'm sorry, similar? And the answer is SAS, similarity. And then it's going to give you this. It's going to say multiple choice. Which of those is the similarity statement, to complete the similarity statement? Okay. Any comments or questions on this example? Oh, there was one other thing I'm going to talk about because Anthony brought it up. By the way, that's a really great t-shirt. That's been a long time. I remember watching that one. I think I was in college. Anyways, okay. The other thing that you could do is you could reduce this fraction, 9 over 21. 3 goes into 9 3 times. And 3 goes into 21 7 times. Now, what's the biggest number that goes into 18 and 42? Turns out that that answer is 6. What is 18 divided by 6? It's 3. You want to take a guess on what 42 divided by 6 is? Now, guys, what do you notice about these two fractions? They're equal, and that's exactly what we mean by things being proportional. They're equal fractions. Okay. So let's go ahead and move on. Let's do another one. In fact, I'm going to give you a little bit of a head start on this one. I've done one. I'd like you to try this one here. I might skip the proof. We'll see. So the question is just like the last one, we're trying to figure out if there's two triangles. Hopefully you can see the two triangles. We want to see if these two triangles are similar. Ooh, that's a weird S. By AA, SAS, and SS or SSS. Okay, I hope you got a little bit somewhere. You maybe aren't finished, but I'm going to just kind of go through this and explain how I would do this problem. Anytime I have like a triangle in a triangle like this, so hopefully you can see that there's this smaller triangle in the bigger one. What I like to do is I actually like to draw them separately. So this is the FSR triangle, and then maybe I'll do it in a different color here. And now I'm going to draw the bigger triangle here in a different color. So there's this one here, and this one is FDE, okay? So there's my two triangles, all right? Now, obviously, this side here is 44. I mean, it says it's 44 right there, right? And obviously, this is 121, so that's easy enough. And I can see that FD is 88, and then that FE is 143. So I've got all three sides of that triangle, so that's great. Now, here's a harder question. What is the length of FR? What is the length of FR? Tomas? It is 52, Tomas. How did you get 52? You got it, buddy. That's exactly right, Tomas. Good job. Guys, we see that FE is 143. We see that RE is 91. So all I need to do to figure out FR is simply subtract. So if you take 143 minus 91, you'll get 52. By the way, this is by segment addition postulate. Similarly, we could subtract 56 from 88, and we'll get an answer of 32 for FS. Now, guys, just looking here, do we know any of the angles? Not really. Now, it turns out that we can actually do this one two ways, but I'm going to try to use this one here, okay? We'll come back to, is there another way to do it in just a second, all right? So here's what I'm going to do. Now, I'm going to show a little bit less work on this one. Let's do it in purple. Okay, 32 is to 88. Do you guys see what I did there? I took the FS to the FD. That was the short side of the first one to the short side of the second one. What was the middle length? What was the middle number? 44, right? So I'm going to put 40. Now, what number do you think I'm going to put on the bottom of 44? No, not 88. We already used 88. 121. And then the long side, which is 52 to 143. All right. Now, what we want to see is, do all of these fractions equal each other? So what I would encourage you to do is, you can, first of all, you can try to reduce, but would you guys agree that it might be kind of hard to reduce those? So let's just do this. Would you take your calculator, just humor me, please. Take your calculator and then cross multiply those two guys and see what you get. I'll do the same. Okay, so I just took 32 times 121, and then I took 44 times 88, so I'm cross multiplying here. I'm going, this times this and that times that. And I got 3872 equals, does 3872 equal 3872? So that's good. Now, I'm going to do the last two guys. Same thing. And I'm going to cross multiply those two as well. Again, very quick thing to do with the calculator, right? So I'm just going to do 44 times 143. And I'm going to do 52 times 121. And here I get 6292 is equal to, and it turns out to be 6292 again. Now, so far, I've only done two comparisons, but that's actually sufficient. If these two guys are proportional and these two guys are proportional, then the first and the third are proportional. So these two triangles are similar by SSS similarity. Now, would you go ahead and finish off this statement right here for me? I haven't done that part. Triangle FED is similar to triangle, and do that last piece there, and then we'll move on. I think I'm going to skip the proof. See if I got time to come back to the proof. Would someone in virtual land please write the three letters, the letters in the correct order for me on this one? Someone in the virtual classroom. What order do I need to put those letters of that small triangle to match up with the letters of the big triangle? Okay, I see FRA. I also see FRS. Anybody else want to jump? Oh, I think Jacob typed the wrong thing if he fixed it. FRS. Okay, so let's try that. Triangle FRS. Let's see if that's right. So our big triangle, or our big triangle here was FED. So that's this guy, right? So FED. So we need to go to FRS. That is correct, Jacob. Thank you, sir. Okay, you guys kind of get a feel for how this AA, SAS, and SSS works. Now, guys, let me just, before I move on to my final example, let me just say this. If you're given a problem, do they always have to be similar? So be careful. I've only done 3 examples in here, so I wanted to do an example of each, right? My first example we did was AA. Second example was SAS. Third example was SSS. And by the way, just to let you know, you could have technically used SAS on this one too, but I'm going to kind of pretend we didn't know that, okay? But it could be that on a Homer problem, it might be that they're not similar. For example, if these two numbers right here didn't equal each other, then they cannot be similar. Okay, so I'm going to skip this example because we're down to about 7 minutes left of class time. Remember, I'm shooting for the first 60 is my time, and then the last 30 minutes is going to be your support time. So I'm going to skip this example. I really want to get to this last example. We talked about one like this last week, not exactly like this, but similar to it, pun intended. One of the biggest, most important ideas when it comes to similar figures is being able to find measures indirectly. What I mean by that is, let me just read the problem. It says that a child, here's the child, is 4.5 feet tall and casts a 6-foot shadow. Here's some statue. We do not know how tall it is, but at that exact same time, at that same place basically, the shadow of that statue is coincidentally just exactly 12 feet. The question is, how can we find the height of the statue? Well, it turns out, first of all, I hope you guys would agree that these are both perpendicular lines. In other words, those are right angles. And it would turn out that the sun is far enough away, these two angles are essentially congruent. In other words, these two triangles are similar. Triangles are similar. That means we can make a proportion on their corresponding sides. In other words, 4.5 is to, what number do you want me to put on the bottom? 4.5, that's the girl's height. What do you want me to put on the bottom? Okay, fine, X. So the girl's height is to the height of the statue, I like that, is to what? What number should I put on the top over here? You got it. And on the bottom? Pretty simple. Can you guys go ahead and figure out what X is in this case? You might need a calculator. Some of you might be able to do that in your head, I don't know. Yeah. So when we cross multiply here, I can make sure I don't do this incorrectly, 4.5 times 12 is 54. And then of course this is 6x. Divide both sides by 6, and you will get an answer of 9. So that means that the height of the statue in this case is 9 feet. Now guys, I know that that's a very simple example and it worked out very nicely, but I'd like you to consider this. Did you know that about 2,000 years ago, there were, by the way, they didn't have calculators back then. They didn't have cell phones back then. They didn't have computers or Google back then. They didn't have satellites. They didn't have telescope. Did you know that they pretty accurately estimated the distance to the moon using a similar technique that we just did right there? It's pretty amazing for me to think. Like they didn't even have paper back then, and they were actually able to use, and they used they used the shadow of the moon basically on the Earth to figure out approximately how far the moon was from the Earth. Now, it wasn't super accurate, but it was a pretty good estimation. So anyways, that's where we're going to stop things today. I'm going to stop recording, and I want to give you guys my exit slip that I would appreciate if you guys would fill out.